In this video, we're going to be deriving the acceleration max of a vertical spring oscillator and a horizontal spring oscillator. So here we have a horizontal spring that is on a frictionless horizontal surface where we have a mass m attached to a spring, and we have a spring constant k that measures the stiffness of the spring. So by Hooke's law, we have that F is equal to negative kx. The negative sign represents that this is a restoring force, and that means that the force is going to be pointing towards equilibrium and is constantly wanting to return to this natural state. So that is going to be why we are going to have an oscillation that is going to be moving the spring from states of being stretched back to its natural state. So we can apply Newton's second law, where the summation of forces is equal to mass times acceleration. So we know that we have negative kx and we have ma. So if we rearrange this for acceleration, we can divide both sides by m, and then we can have that acceleration is equal to negative k over m times x. So how can we find a max from here? We have to find the magnitude of a. So then if we find the magnitude of a, we are just going to get rid of that negative sign essentially. So then it's going to become km over the magnitude of x. So we need to find when the x, aka your displacement, is the largest. So we know that we are going to have the largest displacement when the spring is stretched the furthest. And that is when you're at the amplitude, because your spring is going to follow a sinusoidal path of displacement. So we can see that at its maximum points, that's going to be when it's the furthest away from your equilibrium state of when the spring is at its natural position. So we can see that that's going to be when you're at a, your amplitude, aka when you're at plus or minus a. So now for a vertical spring oscillator, we have that a mass m is going to hang from a vertical spring with a spring constant of k. And then the mass is going to stretch and come to a resting equilibrium position as it always does. It oscillates up and down. So we can find our equilibrium position condition. So when you're at your EQM, that means that with our FBD for our spring, we have that the upward spring force is going to balance that downward weight. So we have that the summation of forces is equal to ma. We're going to have Fs is equal to that upward position. We know that if it's going to be at an equilibrium state, that means that we have the summation of our Fy is equal to 0, aka we have vertical equilibrium. And our Ay is equal to 0. So then we can say that K delta L is equal to mg, because our acceleration is going to be equal to g. So delta L is going to be the equilibrium stretch. So now we're going to displace the mass by y. So if we move the mass a distance y from our equilibrium, then we have that our total spring stretch is going to be delta L plus y. So then the upward spring force is equal to k delta L plus y. But our weight downward is still going to be equal to mg. So if we write our net force, we're going to make our downward as positive because this is going to be the direction of our acceleration. So then we would say that F net is equal to mg minus k delta L plus y, because this is our spring force. And our weight is that mg. So this is our weight minus our Fs. So then we can distribute that spring term. that's going to equal to F net. So we know that at equilibrium, we had that K delta L is equal to mg. So then those are going to cancel. So F net is equal to negative ky. So then Newton's second law states that negative ky would equal to ma. So then if you divide both sides by a here, or if you divide both sides by m, you would get that a is equal to negative k over m times y. So this is the same as simple harmonic motion in the horizontal case. So again, if we wanted to find the max acceleration, that would be a is equal to km magnitude of y. And we know that y is going to be max when you are equal to a, when you're at your amplitude. So that means that if we write a max, that's still going to be equal to ka over m. That's because once displacement is measured from your equilibrium position, your Fg, your gravity, it cancels out. Because our delta x, again, was measured from EQM position. So for both our horizontal and our vertical spring oscillator, A max is equal to Ka over M. Same as over here. A is equal to negative K over M x. So we can write that here without the magnitude. That was AKMX. You can also write this as A max is equal to omega squared A, because omega is equal to the root of K over M. So then if you were to square both sides like this, you would get that omega squared is equal to K over M. So that means that here in this equation, if you took from where you saw Km right here and you replace that, you would get that A max is equal to that omega squared, because we would see K over M right there. So